Limitations of cross-monotonic cost-sharing schemes. As we saw in section 15.3, a cost-sharing scheme that is cross-monotone also satisfies the core property. As a result, for any combinatorial cost-sharing game, an upper bound on the budget balance factors of cross-monotonic cost-sharing schemes can be obtained using theorem 15.8 and the integrity gap examples of the corresponding LP. As we will see in this section, for many combinatorial optimization games, the cross-monotonicity property is strictly stronger than the core property, and better upper bounds on the budget balance factor of such games can be obtained using a technique based on the probabilistic method. The high-level idea of this technique is as follows. Fix any cross-monotonic cost-sharing scheme. We explicitly construct an instance of the game and look at the cost-sharing scheme on various subsets of this instance. We need to argue that there is a subset S of agents such that the total cost shares of the elements of S is small compared to the cost of S. This is done using the probabilistic method. We pick a subset S at random from a certain distribution and show that an expectation, the ratio of the recovered cost to the cost of S, is low. Therefore, there is a manifestation of S for which this ratio is low. To bound the expected value of the sum of cost shares of the elements of S, we use cross-monotonicity and bound the cost share of each agent I in S by the cost share of I in a substructure Ti of S. Bounding the expected cost share of I in Ti is done by showing that for every substructure T, every I in T has the same probability of occurring in a structure S in which Ti is equal to T. This implies that the expected cost share of I in Ti, where the expectation is over the choice of S, is at most the cost of Ti divided by the number of agents in Ti. Summing up these values for all I gives us the desired bound. In the following, we show how this technique can be applied to the facility location problem to show that the factor 1/3 obtained in the previous section is the best possible. We start by giving an example on which the algorithm FL cost share in figure 15.4 recovers only a third of the cost. This example will be used as the randomly chosen structure in our proof. Lemma 15.22. Let I be an instance of the facility location problem consisting of m plus k agents, a1, a2, a3 until am, and m facilities f1, f2, f3, a1 prime, a2 prime, and so on until ak prime. That's the plus k agent, and the m facilities f1, f2, f3 until fm, each of opening cost 3. For every I and j, the connection costs between fi and ai and between fi and aj prime are all 1. And the other connection costs are obtained by the triangle inequality. See figure 15.5a. Then if m is equal to omega of k, and k tends to infinity, the optimal solution for I has cost 3m plus little of m. Prove the solution, which opens just one facility. Say if 1 has cost 3m plus k plus 1, which is equals to 3m plus little of m. We show that this solution is optimal. Consider any feasible solution that opens f facilities. The first opened facility can cover k plus 1 agents with connection cost 1. Each additional facility can cover 1 additional client with connection cost 1. Thus, the number of agents with connection cost 1 is k plus f, and the remaining m minus f agents have connection cost 3. Therefore, the cost of the solution is 3f plus k plus f plus 3 times m minus f, which is equals to 3 times m plus k plus f. As f is greater than or equals to 1. This shows that any feasible solution costs at least as much as the solution we constructed. Theorem 15.23, any cross-monotonic cost-sharing scheme for facility location is at most 1/3 budget balanced. Proof: consider the following instance of the facility location problem. There are k sets A1, A2, A3 until ak of m agents, each where m is equals to omega of k, and k is equals to omega of 1. For every subset B of agents containing exactly one agent from each AI, such that the intersection between B and the AI is equals to 1 for OI. There is a facility FB with connection cost 1 to each agent in B. The remaining connection costs are defined by extending the metric, that is the cost of connecting agent I to facility FB for I not in B is 3. The facility opening costs are all 3. We pick a random set S of agents in the above instance as follows. Pick a random I from 1 to 3 among 1 to 3 until k, and for every j which is not equal to I, pick an agent aj uniformly at random from capital AJ. Let T equals to the set of aj such that index j is not equals to index I, and S is equals to AI union T. So see figure 15.5b. For an example, it is easy to see that the set S induces an instance of the facility location problem almost identical to the instance I in lemma 15.22. The only difference is that here we have more facilities, but it is easy to see that the only relevant facilities are the ones that are present in I. Therefore, the cost of the optimal solution on S is 3m plus little o of m. We show that for any cross-monotonic cost-sharing scheme, C, the average recovered cost over the choice of S is at most m plus little of m, and thus conclude that there is some S whose recovered cost is at most m plus little of m. We start by bounding the expected total cost share using linearity of expectation and cross-monotonicity. That is, the expectation S of, for S of the summations of C of AS, summing for all A in S, is equals to the expectations of the summations of C of AS, summing for all A in AI, plus the expectations of the summations of C of AJ as summing for all j which is not equals to I, which happens to be less than or equals to the expectations of the summations of C of A and the singleton A union T, summing for all I, A which is in AI, plus the summations of the expectations of the summations of C of AJ T, summing for all index j which is not equals to I. So notice that the set T has a facility location solution of cost 3 plus k minus 1, and thus by the budget balance condition, the second term in the above expression is at most k plus 2. The first term in the above expression can be written as m times ESA of C of A and the singleton A union T, where the expectation is over the random choice of S and the random choice of A from AI. This is equivalent to the following random experiment. From each AJ, pick an agent AJ uniformly at random, then pick I from the set 1 to 3 until k uniformly at random, and let A equals to AI and T equals to the set AJ such that J is not equals to I. From this description, it is clear that the expected value of C of A and the singleton A union T is equal to 1 divided by k times the summations of C of aj enters the set a1, a2, a3 until ak, summing for all index j which start from 1 to k. Thus, by the budget balance property and the fact that the set a1, a2, a3 until ak has a solution of cost k plus 3 cannot be more than k plus 3 divided by k. Therefore, ES, the expectations of S of the summations of C of AS, summing for all A in S, is less than or equals to M times k plus 3 divided by k, then plus k plus 2, which is equals to M plus little of m. This is 15.6, where m is equals to omega of k and k is equals to omega of 1. Therefore, the expected value of the ratio of recovered cost to total cost tends to 1/3.